the computational procedure basically go like this. First, we compute the innermost product. In other words, from here to there, which is W raised to the power N0 K2 R2 R3 multiplied with the summation on F K2 K1 K0. That product, we call it the vector F1, intermediate vector F1. After you compute the intermediate vector F1, the next thing we take the summation on the index K1 times F1 and multiply with W raised to the power N1 R1 plus N0, the whole thing K1 R3. That together will give you the intermediate vector F2, as I show you in the green color. And finally, after calculate F2, we take the summation of the index on K0 and we multiply with that term W raised to the power N2 R1 R2 plus N1 R1 plus N0, the whole thing K0, together will give you the intermediate vector F3. Now, again, the reason you have to compute three computational vector F1, F2, and F3, the reason is because we say right now we assume capital N is equal to three integer product R1, R2, R3, and that's why you have three intermediate vector F1, F2, F3. Now, by the time that you finish the computational of vector F3, what you get will be the answer for the unknown vector C tilde, except you have to reverse the bit through the unscrambling process, like I said to you many times before. So that is the idea, and you can see on the next slide that just repeated what I just told you. First, you do the summation on the index K2. Now remember, in equation 90, the function f corresponds to K2, K1, K0. That function is known. That is a given periodic function corresponding to the discretized time expressed as K2, K1, K0. After you calculate equation 90 to obtain the intermediate vector F1, then the next step you say go to equation 91, the one in red color. We just compute the vector F1 based on equation 90. We multiply with W raised to that power. Then we can compute the intermediate vector F2 as I show you in the red color in equation 91. Finally, after computing F2 in equation 91, we plug that into here in equation 92. We multiply with W raised to that power as shown in equation 92 in blue color. Then that will give you the intermediate vector F3. And like I told you before, the intermediate vector F3 is basically give you the unknown vector C tilde, except the order are different, because in F3 the order is N0, N1, N2, where the unknown vector C tilde, the order is N2, N1, N0. And that's why after you obtain the vector F3, you have to go through the reverse order to go through the so-called unscrambling process that I discussed to you earlier in my previous lecture, in order to obtain the unknown vector C tilde in the right order. Now, in this chapter, we consider the number of sample data point capital N expressed in terms of the product of 3 integer. Again, there's a typing error in here. This n should be R1 time R2 time R3. In this particular chapter, we consider R1 is equal to 2, R2 is equal to 2, and R3 is equal to 2. So capital N is equal to 8. In much earlier chapter, when we talk about the informal fast Fourier transform, we say the number of sample data point has to be expressed in terms of 2 raised to the power 3, where 2 raised to the power r, where r could be any integer number. So if you let the power r is equal to the integer 3, then you also get capital N is equal to 8. Here, capital N is equal to 2 times 2 times 2 is equal to 8. So what does that mean? What it means is that the formula or the procedure that we develop in this particular chapter right now, based on capital N is equal to the product of 3 integers, should be exactly the same or identical to the formula that we developed earlier corresponding to n equal to 2 to the power r, assuming r1, r2, r3 each equal to 2, and assuming r is equal to 3. They should be identical. Then the reason, because both k corresponding to the number of data point capital N is equal to 8. So in order for us to see the connection or the relationship between this general fast Fourier transform algorithm based on the product of R1 times R2, R3, again there's a typing error in here, n should be equal to R1 times R2 times R3, compared to the so-called base 2 fast Fourier transform algorithm, such as n equal to 2 raised to the power r. We consider the situation where R1, R2, R3 each equal to 2. Now let's see what happened when R1 equal to R2 equal to R3 and equal to 2. Well, there's a typing error here again. The capital N, it should be equal to R1 time R2, not comma, time R2 time R3. Okay? In this case, then equation 90, 91, 92 that we developed earlier, few slides ago, can be simplified to equation 94. Well, in case you don't see it, let's go back to equation 90, 91, 92. Let's see. Equation 90, 91, 92. You see that? This is equation 90 to compute the first intermediate vector f1. Equation 91 compute the second intermediate vector f2. Equation 92 compute the third vector f3. So if you look at these three equations, and whenever you see R3, you replace by 2. Whenever you see R2, you also replace by 2. Whenever you see R1, you replace by 2. R3, you replace by 2. Whenever you see R1, you replace by 2. R2, you replace by 2. R1, you replace by 2. In other words, whenever you see R1 or R2 or R3, you replace by 2. Then also notice, because R1 you replace by 2, that means this summation that you see here on the index K2 of equation 90, that summation K2 will go from 0 to 1. Similarly, because R2 is equal to 2, therefore the summation on the index K1 that you see in equation 91 is also have K1 go from 0 to 1. And again, because R3 is equal to 2. So the summation on the index K0 is also going from 0 to 1. So equation 90, 91, 92, after you substitute R1, R2, or R3 each equal to 2, then they will become more simple, like equation 94, 95, and 96. And actually, if you compare equation 94, 95, and 96, and you compare that to the earlier that we derived equation 22 to 24, those equations 22, 23, 24 was based on capital N is equal to 2 raised to the power 3, which is 2 assuming r equal to 3. They are identical to equation 94, 95, 96. So this chapter basically give you the formulation or the derivation for the number of sample data point is equal to the product of any three integer. And for that matter, you can generalize even further. For instead of having three product, you can have M product. R1, R2, R3 times R4 times R5, blah, 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 all the way up to R sub M. And that is the end of this lecture. Here is the acknowledgement.